My name is Josh Gargan, and this is my presentation on circuits and capacitors. We have seen how protons and electrons can generate their own electric fields and can also generate their own magnetic fields if they have an initial velocity. Circuits act as a medium connecting our physics concepts to practical applications in the real world. Circuits act as a path which electrons can flow through. For simple circuits, the electric field is equal in magnitude along the circuit, but the direction follows the current. The two important laws surrounding circuits are the node rule and the loop rule. The loop rule says that the potential for a round trip across the circuit must equal 0, and the node rule says that when the current diverges at a node, the current coming in equals the sum of the currents going out. We have already learned that electric potential is a measure of the potential difference between two or more points in space due to other objects in surroundings, such as other charged particles. Circuits show us a more practical reason for understanding the potential difference across different portions of the circuit. The measure of the potential difference for a battery comes from some non-electrical process. A resistor is a device which resists the flow of electrons. A capacitor is a device in which two plates are separated by some tiny distance, and charge builds up on both sides of the plate as it is charged. The diagram shown is the type of circuit I had to set up in the PhET simulation. I calculated both currents prior using the node rule and the loop rule, resulting in a value of 0.02 amps for both currents. The ammeter read the same, and reversing the ammeter didn't change the value shown. When I replaced an ammeter with a voltage meter, the current went to 0 because the circuit was open, and the voltage read 3 volts instead of 0 volts because the potential difference between the two ends of the circuit depended only on the EMF from the batteries, given there was no current to flow through the resistors. I then measured the change in potential difference across different portions of the closed circuit and found that the total potential equals 0 volts due to the loop rule. When the voltage meter was attached to the closed circuit, the ammeter didn't change because current wasn't flowing through the voltage meter. The voltage meter only measured the potential difference between 2 points, not acting as an alternative route for the circuit. Placing the ammeter parallel to the 100 ohm resistor caused a short in the circuit, meaning an easier path was created that the electrons would flow along. This meant no current flowed through the 100 ohm resistor, and the current value went up from 0.02 amps to 0.06 amps. The resistance for the two resistors, the wire, and the ammeter were calculated and shown. An RC circuit is a circuit which consists of a resistor, in this case a 10 ohm light bulb, and a capacitor. When the circuit is connected, the light bulb comes on, but over time the light begins to dim and eventually goes out. Initially the capacitor acts just as a wire in the circuit, and the light comes on, but over time charge builds up on the two plates and the current eventually drops to 0. When the capacitor is connected directly to the light bulb, the light comes on and eventually goes out, as all the charge is released from the plates. Using the data I collected from the simulation, I plotted the decrease in voltage over time. The graph seen on the left is an exponentially decreasing function with respect to time. To determine the value of RC when the voltage has dropped to 1 over E of its original value, I altered the data to create a linear regression plot whose slope is negative 1 over RC. The RC value was approximately 5.94 seconds, and the voltage at that point was 3.31 volts. If this lab were done in real life with an actual ammeter instead of an idealized ammeter, I would have found that the ammeter would have behaved like a resistor. In reality, all components in circuits have some amount of resistance, meaning the actual current shown would have been smaller than that found using an idealized ammeter. If the lab were done in real life with a real battery to charge a real capacitor with no resistor in the circuit, the capacitor would theoretically charge almost instantaneously and stop the flow of electrons through the circuit. In the real world, there would be some amount of resistance in the wire and the capacitor, so the capacitor would take more time to charge than an ideal circuit. Thanks for watching.